Alright everybody, now we're going to take a look at the two practice problems in this handout. We're going to look at problems 2 and 3. So problem 2, we have two spherical tennis balls here, right? They're usually sold in cans like this here. You got two in a can like this. The balls happen to be tangent to each other, as well as tangent to the lateral surface, and as well as one base of the can. So this top ball here is tangent to the surface of the can, as well as the upper lid, and this bottom one is tangent to the top one and the bottom surface. We want to determine the fraction of the volume of the can that the two balls occupy here. So in this case here, since we aren't told anything, but we know that we're trying to find a volume here, that makes things a lot easier. So let's call the radius of any one of the spheres r. So it shouldn't be too hard to show here that this cylinder should also have a radius of r. Now the height of the can, well, we have to figure this out. Well, in this case here, because it's two balls to this can here, we know this is going to be 2r up here and another 2r up here, so it makes sense that the height of the can here, the height of the cylinder, is 4r here. So therefore, now all we need to do is just calculate this volume here. So compute the fraction of the volume of the can that the two balls occupy here. So our fraction here, well, let's see. Let's take a look at our denominator. Our denominator is going to be the volume of the can here, and that's pretty straightforward. Volume of the can is just simply pi times r squared times the height, which in this case is 4r. And the numerator here is going to be two spheres here. So one sphere is just 4/3 pi r cubed, but there are two of them, so we're going to have two copies of that. So it's just a matter of whatever this fraction is going to be. Okay, so the first thing to note here is there's a pi in each of these, and they're going to drop out very nicely. We have an r squared times, so let me go ahead and multiply this out. This becomes 8/3 times r cubed divided by 4r cubed. And the nice part about this is you can see the r cubes dropped out here. And then we have just 8/3 divided by 4, which is really 8/3 times 1/4. So you can drop these out here. So this is going to be a 2 and this is going to be a 1. And we're left that the spheres take up 2/3 of the volume of the can. Okay. Problem 3 is an old problem from an AMC from the 80s. You have a spherical ball floating in a lake, and the lake freezes. So, this is, there have been situations where nights have been so cold that I've actually seen birds have their feet frozen to the ice where they once stood. It's a really sad spectacle. So the idea here is that we're going to remove the ball from the ice, and what's left in the ice here is going to be an indentation. So there's going to be a circular indentation here, and the hole has a depth of 8 and a width of 24. So basically, what ended up happening is something like this here. Let's say this is our sphere. Right, so we're going to look at it from the side here. So instead of looking from the top down, we're going to look at it from the side. And this here is the surface of our water. Now, the surface of the water freezes, which means it becomes nice and flat here. So this is nice and flat. And now we can see that this is going to be our case here. So basically, we can imagine that this is going to be our ice here. Now this is all ice down here as well, but there's also ice up here as well. And that's going to be the most important part. So we're told that the hole here, this hole has a depth of 8 and it's 24 centimeters across. So if we look at the sphere here, right, you'll note that, again, just like any other good 3D problem, we're going to collapse this into 2D to make this easier for ourselves. So in this case here, there's some specific points here. I'm going to draw this radius here. I don't know what the radius is, but we can calculate it. Right? I'm going to call these 2 points here A and B. Here's the center O, and this point down here I'm going to call it C, where the bottom of the sphere was in the water. So we note that in this situation, we're told that this intersection point, let's call this D. We know that DC is 8, and the hole is 24 across. That's AB. Now note that in this situation here, we're going to have a right angle like this because of the way it's set up here. We can say that the ball's perpendicular to the surface of the water here, and it works out really well. So that means this here is going to be splitting this in half, so this 12 and this 12. So now we have a nice little thing here we can take a look at. We can draw an AO now. Now we know that AO is the radius of the sphere. OC is also the radius of the sphere, so it's also R, but this is 8, so therefore this is R minus 8. So what I have here now is triangle ADO. We can now yank out triangle ADO here. This is 12, this is R minus 8, and this is R. Again, that comes from this sphere here. So we can now do the Pythagorean theorem. So we get 12 squared plus R minus 8 squared equals R squared here. So let's see, that's 144 plus R squared minus 16R plus 64 equals R squared. We note the R squareds drop out, which is wonderful, and that's what we want. So now the 16R is going to go on the right-hand side. The left-hand side is just 144 plus 64. Now, 140 plus 60 is 200, and we have another 4 here. That's 208. So therefore, the radius is just 208 over 16, and I think we can simplify this here. We know we can yank out a 4 of each of these for sure. So 208 divided by 4, let's see. Well, let's see. 200 divided by 4 is 50, and 8 divided by 4 is 2, so this is 52. And then we can see here, wait a minute, that actually works out really well. So the radius of the ball is therefore 13.